أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. Assalamu alaikum students. So the paper which we'll be doing today is Chemistry 9701, paper 4. The variant is variant 2, so paper 42, May June 2024, paper 4. This paper is for 100 marks and for 2 hours. So let's start. We will be starting with question 1. Now, let's carefully understand what the question is trying to ask us. It asks us, firstly, we need to underline the command words, describe and explain. Okay, so now it's asking us to describe a phenomena and then explain the phenomena using the knowledge that we have. Describe the trend in the solubility of the sulfates of magnesium, calcium, and strontium. If you have been learning correctly, and according to the syllabus, we should know by this point that solubility of sulfates decreases on the way. We already know this. The question is for 4 marks, which means that we need to plan. Whenever a question is for 3 or more marks, we need to plan before we write an answer. So it's asking us about solubility and sulfates. So we obviously know that group 2 sulfates solubility decreases down the group. Now we know that. Meaning that if we look at the periodic table, magnesium, calcium, and strontium, magnesium will have the highest solubility, which is magnesium sulfate, and strontium sulfate will have the lowest solubility. We already know that. So we described the trend. Now we need to explain the trend. Let's first write this trend over here. MgSO4, CaSO4, and SrSO4. Now, how did I get this chemical formula of SrSO4? The thing is, this is an ionic compound wherein we have a metal ion and a polyatomic ion, which means that in order to find out the correct chemical formula, we need to do crisscross. Therefore, I will write Mg here, SO4 here, Mg typically exists as a 2 plus ion, and SO4 is a sulfate ion which exists as a 2 minus ion. When I crisscross, this becomes Mg2SO42. I can just simplify it to make it MgSO4. The same case is with calcium as well as strontium. Now I know the chemical formula, I know the solubility, and I know the trend. I've written that. Now, let's just first write the trend. Solubility of group 2 sulfates, solubility of group 2 sulfates decreases down the group. Now, we already have gained 2 marks, one for writing the trend and one for describing it. The other 2 marks are for 3 keywords which we need to include in an answer. The first keyword is lattice enthalpy. Second keyword is hydration enthalpy. And the third keyword is enthalpy change of solution. Now, if the solubility was increasing, if the solubility was increasing, then we would say that the enthalpy change of solution becomes more exothermic down the group or more negative down the group. But here we're talking about sulfates. So because the solubility is decreasing down the group, we will write the enthalpy change of solution becomes more endothermic or more positive down the group. Now we know enthalpy change of solution becomes more positive. Just write it in short form in your notes so it makes it easier. This is done. But before that, we have to talk about the lattice enthalpy and the hydration enthalpy. Now just think for a moment. If the solubility is decreasing, which of these two variables will decrease more faster or will decrease at a greater amount? It is the enthalpy change of hydration which will decrease at a greater amount. Because if you think about it, enthalpy change of hydration simply means that when ion dipole forces are formed between the gaseous ions, for example, if I have a sodium ion, it's an Na plus gaseous ion, which is surrounded by four water molecules, instead six water molecules. This is ion dipole forces. Sorry, this is not ion dipole forces, but when I just drew three water molecules, instead there are six water molecules around this gaseous sodium ion. Now, the lone pair of electrons on one lone pair of electron on each of the oxygen atom present in each water molecule forms an ion dipole force. And bond forming is exothermic. When the bond forms, energy is released. So, if the solubility is decreasing, then shouldn't this bond, this ion dipole force, get weaker? Which means that the enthalpy change of hydration should decrease more rapidly than the lattice enthalpy. Yeah, I'll repeat. If what is hydration enthalpy? Hydration enthalpy is when ion dipole forces are formed between the gaseous ion and the lone pair of electron present on the oxygen atom in the water molecule. If solubility is decreasing, this bond should get weaker and making it difficult to go from a gaseous ion to an aqueous ion. So now we know that hydration enthalpy decreases, lattice enthalpy also decreases, but hydration enthalpy decreases more rapidly. So now we'll just write that down. Both enthalpy change of hydration. I'm just writing it in short form. In the exam, you would have to write the whole thing. Both enthalpy change of hydration and lattice enthalpy decrease down the group. But enthalpy change of hydration values decrease more rapidly. Enthalpy change of hydration values decrease more rapidly, causing the enthalpy change of solution values to be more endothermic down the group. Simple as that. 4 out of 4. Now, next question. Define lattice enthalpy or define lattice energy. This is simple. Definitions where it says the word define is absolutely free marks. You learn this and then you come into the exam and write it straight away. You don't need to think about it. So what is lattice energy? It refers to the amount of energy released when gaseous ions react together, forming one mole of ionic solid. Simple. Just as an explanation, an example of this could be sodium gaseous ion and the chloride gaseous ion reacting together to form one mole of ionic solid, which is sodium chloride. Simple. We don't need to write this equation, it's just for your explanation. Uh, right. The next question says to yeah. State and explain the main factors that affect the magnitude of lattice energies. Now you should know this by heart at this point. The two things. Simple. The first thing is the charge on the ion. Now, what do I mean by the charge on the ion? Let's try explaining it. Firstly, in order to understand what do we mean by charge on the ion, we need to understand by what do we mean by lattice energy. If I have gaseous ions reacting with each other, now what do we mean by reacting with each other? When I say reacting with each other, I mean forming ionic bonds with each other. When gaseous ions form ionic bonds with each other, they form ionic solids. So when gaseous ions react together to form one mole of ionic solid, the energy release is called lattice enthalpy. Now let's take an example. I have Na plus and Cl minus, and I have Ca2 plus and Cl minus. In both cases, I have the chloride ion, so its effect is cancelled. But in one case, I have sodium ion. In the other case, I have a calcium ion. Now, in which case would the chloride ion be attracted more strongly? Will it be attracted more strongly to the sodium ion or the calcium ion? To the calcium ion. Why? Because a calcium ion has a +2 charge, it would be able to attract the chloride ion more strongly. So, if it attracts it more strongly, then stronger ionic bonds formed. If stronger ionic bonds formed, then the lattice energy would be more negative or more isothermic, which means its magnitude would be higher, which the question asks us. So, the first, and this is the most important factor. The other factor is less dominant. Now, what do I mean by less dominant? If I have such a situation wherein Na plus Cl minus and Cl2 plus and Cl minus, I will look at only charge on the ion, not the size of the ion. Which brings me to my second point. The size of the ion is the second factor, but again, it's the less dominant factor, meaning in any question asking about factors, or there are some questions which ask which has a more negative lattice enthalpy, I will always look at which one has a greater charge. If same charge, then I move forward and look at the size. Whichever one has a smaller size will be able to attract it more strongly. Let's understand this. Let's take an example of two ions which have the same charge but different sizes. For example, sodium and potassium. Right. So I take Na plus Cl minus, and K plus. Sodium has a smaller size. Potassium has a bigger size because, as we know, as we have learned in AS level, the size of the ion increases down the group. Now, in which case would the charge be concentrated, and in which case would the charge be spread out and it would be more dilute? In the case of sodium, both have the same charge, but in the case of sodium, the charge is spread over a smaller area. So it will be able to attract the chloride ion more strongly. In the case of potassium, it has a bigger size. Charge is spread over a larger area. So attracting the chloride ion would be difficult, which means that weaker ionic bonds are formed. If weaker ionic bonds are formed, then lesser energy is released. If lesser energy is released, which obviously means that lesser lattice enthalpy or lattice energy. So we need to state and explain the main factors that affect the magnitude of lattice energy. The first one would be the charge on the ion. So, as we stated, the greater the magnitudes of charges, and in every case, in every question, they will keep, in this case, they're not asking about a specific ionic compound or a specific formula unit, but when they do, they will always keep a particular ion same so that you can cancel them out and you can focus on the other ion. Either they will keep the cation same or they will keep the anion same. So the greater the magnitude of charge, pardon my writing, I'm just writing it to be quick and to be able to explain more. So the greater the magnitude of charges on the ions, the stronger the electrostatic forces developing between oppositely charged ions. Whenever there is a force between oppositely charged ions, it's called electrostatic forces. So developing between I'm just writing in short form. Please write it in long form in the exam. Developing between oppositely charged ions, the higher magnitude of lattice energy. Now, the second thing would be the second factor, in fact, would be the size of the ion. Now, the greater the ion size, the bigger the ionic radius. Let me explain what I mean by ionic radius in just a second. The bigger the ionic radius, weaker forces develop, lower magnitude of lattice enthalpy. What do I mean by ionic radius? This is the nucleus of a sodium ion. This is the nucleus of a chloride ion. The distance, the distance from one nucleus to the next in one formula unit. What is a formula unit? A formula unit means one cation and one anion. So the distance from one nucleus to the other in a formula unit is called ionic radius. When the size of an ion is small, obviously it is closer to the chloride ion or the anion, whatever. which means that the ionic radius is automatically going to be smaller, correct? So smaller ion size, smaller ionic radius, more weaker electrostatic forces of attraction develop, lower the magnitude of lattice enthalpy. Right. In the next question, table 1.1 shows some energy changes, blah, blah, blah. Okay, we look at them. Next, Born-Haber cycles. Okay, it's asking about a question from Born-Haber cycles. They can be used to determine the lattice energies of ionic compounds. Complete the Born-Haber cycle for potassium sulfide. Okay. Oh, this is the one thing we have to take care of, and this is the other thing that we need to include state symbols for all of the species. It's a simple enough Born-Haber cycle. A Born-Haber cycle, remember, always has two roots. One root is this one, and the other root is the longer one, this one. So this is one root, and this is the second root. They have already completed one root for us. We need to complete the second root, which is the longer one. Let's do that. Now, when you attempt a Born-Haber cycle, there should be some ground rules that you should know. Whenever you need to remove an electron or you need to add an electron, every single time the species needs to be in a gaseous state. You cannot say that this is sodium solid form becomes Na plus solid. No, that's not how this works. Every single time the species has to be in a solid form, in a gaseous form in order for it to be able to remove or add an electron. So now I need to go to a potassium ion from a simple potassium species, which means that I need to remove an electron. But wait, in order to remove an electron, I need to turn it into a gaseous form. How do I turn it into a gaseous form? Enthalpy change of atomization. Enthalpy change of atomization is when one mole of gaseous atoms are formed from its constituent element under standard conditions. I repeat, enthalpy change of atomization is when one mole of gaseous atoms is formed from its constituent elements under standard conditions if it is standard enthalpy change of atomization. One mole of gaseous atoms formed from constituent elements under standard conditions. See, solid converts to gaseous. Now, what if I have 2Na becomes 2Na? The enthalpy change of atomization value becomes multiplied by 2. Because what was the meaning of atomization? One mole of gaseous atoms. Therefore, if I have two moles of gaseous atoms, atomization value multiplied by 2. So now I have two potassium solid, which I need to convert to 2 potassium gas. Let's do that. 2K gas. Now I'll not touch the sulfur. I'll keep it as it is, and I'll look at it when I talk about sulfur later. First, I need to take care of potassium, not sulfur at all. So this was now it's not asking us to label the arrow, but we can do it for our own help. This is going to be enthalpy change of atomization multiplied by 2 in order to reach from this to this. Next, I need to make each mole of potassium lose one electron. Like if it was K gas and it becomes K plus gas plus electron released, it is one mole of potassium has lost one mole of electron to form one mole of potassium ions, which has a plus one charge, right? One mole of potassium in its gaseous form has lost one mole of electrons to form one mole of potassium ions, which has a plus one charge. Therefore, I can just multiply the entire equation by 2. Now I have 2 moles of potassium, and I need to lose 2 moles of electrons, one from each, to form 2 moles of potassium ions, which have a plus one charge. So this becomes 2K plus gas. See, I reached it, plus S solid plus 2E minus. So what was this? This was ionization energy of potassium times 2. Now students do this mistake when it says 2 potassium and then when they need to go to 2 potassium ions, they take the first ionization energy and add it with the second ionization energy. No, this is not the case. You are going from a zero charge to a plus one charge. It's only the first ionization energy that is involved. Now, if I put 2 here, I multiply it by 2. If I put 20 here, I multiply it by 20. If I put 100 here, I multiply it by 100. If I say to go from 0 to 2 plus, then it would be first ionization energy plus second ionization energy because now I have lost 2 electrons. But here I've only lost 1 electrons per mole. So that is first ionization energy multiplied by 2. Now I have taken care of potassium. I have lost the 2 electrons from potassium. Now I need to take care of sulfur. The only thing I need to do is convert it from a solid to a gaseous state. And what is that? Enthalpy change of atomization of sulfur. This was of potassium. Now then, I need to make sulfur gain 1 electron, and then here I need to make it gain another electron. Let's look at this. This becomes 2K plus gas plus S minus gas. Now I have made it gain 1 electron. 1 electron is left. So I write plus and minus. What was this? This was first electron affinity of sulfur. Obviously, sulfur is gaining the electron. Now you can write the first and second at once, but here because they have given two blanks, so I will gain the electron one by one and not both at once. I can do that, but it's two blanks and it's more better to fill both of those blanks. So 2K plus gas plus S2 minus gas. Now there's no need to write the electron because that is already being gained. This is the second electron affinity. And now when I go from this to this is simply lattice enthalpy. 1 mole of ionic solid formed from its gaseous ions reacting together. Lattice enthalpy. Simple, simple. Did we write the state symbols for each case? Yes, we did. So this is done. Bond neighbor cycle is also done. Now we need to calculate the lattice energy of K2S using the relevant data. Now what do we do here is we create a simple equation. On the left hand side of the equals to sign, we write about one root, and on the other hand side of the equals to sign, we write about the other root. What do I mean by that? This was one root, so I write it. Okay, what is this? This is the enthalpy change of formation. So I write about the enthalpy change of formation, and because 1 mole is being formed here, I just keep it as it is. I don't need to multiply it by anything. Right, let's look at the enthalpy change of formation for potassium sulfide. There we go. It's minus 381. So I'll write minus 381 is equal to, now I will look for the enthalpy change of atomization of potassium and also multiply it by 2. Atomization of potassium is 89 times 2. So I'll say 89 times 2, and it's always going to be positive. Why is that? Because bonds are breaking. You're going from a solid to a gaseous state. Bond breaking is endothermic. That's why it is always, always positive. Right. Plus ionization energy times 2. What is the ionization energy of potassium? The first ionization energy is 419. So I just write 419 times 2. This is done, this is done. Always keep ticking so you know where you are right now and you don't mistakenly add the same thing 2 times. Enthalpy change of atomization of sulfur. So this is 279 times 2. Or is it times 2? It's not times 2. So it's just plus 279. Then is the first electron affinity of sulfur. First electron affinity of sulfur is minus 200. Second electron affinity is plus 640. Minus 200 plus 640 plus the lattice enthalpy because that's the value which I have to calculate. Treat it as a simple simultaneous equation, or treat it as a simple single variable equation, and then the lattice enthalpy comes out to be minus 2116 kilojoule per mole. This becomes minus 2116. Now in All right. Now, one mistake that students do is while writing this single variable equation, they say, oh, lattice enthalpy is supposed to be negative. So why shouldn't I write this as minus lattice enthalpy? The thing is, when you write minus lattice enthalpy, the answer will become plus 2116 kilojoule per mole. At that point, you should have the common sense to say that lattice enthalpy, bro, it's exothermic. Lattice enthalpy is exothermic, which means that it's negative. So 2116 can never be the answer. So just put a minus sign next to it. Simple. Or in order to avoid all of this confusion, just write plus lattice enthalpy as if you are plusing the entire thing or adding the entire thing. Right. Next question. Next question we have here is lithium nitrate decomposes on heating in a similar way to two nitrates to give the metal oxide, a brown gas, and oxygen. Write an equation for decomposition of LiNO3. So it gave us a clue that it heats and decomposes in fact in a similar way to group 2 nitrates. I've written an example of group 2 nitrates decomposing. Let's say calcium nitrate. It becomes calcium oxide plus nitrogen dioxide plus oxygen, and this is an unbalanced equation. It's a simple 1 mark question, no need to spend a lot of time. Lithium nitrate becomes lithium oxide. In fact, this becomes Li2O when we crisscross plus nitrogen dioxide plus oxygen. Now, if I need to balance it, I put a 2 here, a 2 here, and half here. Or I could also do this. I could put a 4 here, a 2 here, 4 here, and just keep it as it is. I can just multiply the entire equation by 2. So all of the coefficients become multiplied by 2. Now, the other group 1 nitrates The other group 1 nitrates, metal nitrate, N stands for metal. The other group 1 nitrates, metal nitrate, decompose on heating to form the metal nitrite, which is MnO2 and oxygen. And the thermal stability of the nitrates increases down the group. Now, the question this is not the question. The question is why the thermal stability of metal nitrate increases down the group. We need to give the same explanation which we did for the thermal stability of group 2 nitrates, which we learned about the thermal stability of group 2 nitrates, apply the same knowledge to group 1 nitrates. Because it already said that group 1 nitrates decompose on heating in a similar way to group 2 nitrates. It already gave us a similarity between group 1 and group 2 nitrates. And we are going to use this similarity here. See, we learned about group 2 nitrates, but we are applying it on group 1 nitrates. This is how students get confused. So, exact same knowledge, instead of group 2, we write group 1. We will say that the size of group 1 metal ions increases down the group. So, what happens? Simple. The polarizing power decreases. This is the first keyword that we have to use to get 2 marks. Polarizing power decreases. If the polarizing power decreases, the polarization decreases. The polarization of what? The polarization of nitrate ion decreases down the road. So the thing which is happening here is I have taken a container and I have added X 250 cubic centimeters of it to 50 cubic centimeter of manganate ions. Let's read further. The manganate ions are in excess. What does that mean? That X is the limiting reagent. It ensures that all of X completely reacts. Now we know that X completely reacts because manganate was in excess, which means now we can use the stoichiometric ratio in order to find out the final answer. All of the nitride ions are oxidized as we predicted. So now we also know that manganate ions are reduced. Let's just write all of this. MnO4 minus is reduced. X is the limiting reagent. Right. The unreacted, obviously it was in excess. Some of it reacted with X and some of it was left. So now the unreacted MnO4 minus required this much Fe2 plus to reach the endpoint. The relevant half equations are shown. Now, two reactions have taken place here. This is the first one, this is the second one. Half equations are given for both of these reactions. What do I have to do? I have to calculate the concentration in mole per decimeter cube of NaNO2 in X. Let's start backwards. Firstly, let's calculate the moles of Fe2 plus. This will make sense in just a moment. Number of moles of Fe2 plus equals. Now you should know the formula. N is equal to Cv over 1000, which means that 22.5 times 0.04 divided by 1000 will make 9 into 10 to the power minus 4 moles. Now I have found the moles of Fe2 plus. But wait, I cannot do the stoichiometric ratio of going from Fe2 plus to MnO4 minus. Why is that? Because the equation is not balanced. When can I do the stoichiometric ratio? When I know what is the limiting reagent and what is in excess, I know that. But I need to know the balanced equation. And how do I know that it is not balanced? 5 electrons and 1 electron. This is how I know this is not balanced. So let's balance it. Multiply this entire equation by 5. Becomes 5 Fe2 plus to give 5 Fe3 plus 5 electrons. Now multiply this entire equation by 1, making 5 electrons and 5 electrons. Now I'm going from 5 Fe2 plus to MnO4 minus. Let's just write this here. If the moles of 5 Fe2 plus were 9 into 10 to the power minus 4, I want to go to, this is not a equation, this is simply a mathematical equation. I want to go to MnO4. Again, I repeat, this is not a chemical equation. This is not a reaction that is taking place. Instead, in the real reaction, both of these are reacting. What's the ratio right now? 5 is to 1. Now let me just write 9 into 10 to the power minus 4 here and x here. 5x, this is the butterfly method, is equal to 9 into 10 to the power minus 4. X becomes 9 into 10 to the power minus 4 divided by 5. So the purpose of doing all of this was to show how stoichiometric ratio works. I went from 5 moles to 1 mole by dividing this with 5. Now I know the number of moles of unreacted MnO4 minus, which is 9 into 10 to the power minus 4 divided by 5, which is 1.8 times 10 to the power minus 4 mole. Now let's understand something. I had the total moles right here. I can just do Cv over 1000. I have the unreacted moles also, which means that if I do total minus unreacted, what will I get? I will get the reacted moles, which have reacted with X. Let's just do that. But before that, I need to find the total moles. So the number of moles of total MnO4 minus is equal to Cv over 1000. 50 times 0.125 divided by 1000, which is equal to 6.25 times 10 to the power minus 3. This was the total moles. This is the unreacted moles. When I minus 6.25 times 10 power minus 3 from 1.8 times 10 to the power minus 4, what am I left with? I am left with 6.07 times 10 to the power minus 3. What is this? This is the moles. This is the moles that reacted with X. Now, it's time to do another stoichiometric ratio to go from manganate ions to nitrite ions. But can I do the stoichiometric ratio? No, because 5 electrons and 2 electrons. Let's balance these two equations this time. I multiply the entire equation by 2.5, which makes this 5, makes this 5, makes this 5 by 2, which is 2.5. This becomes 5 by 2, and this becomes 5 by 2. So now, if I want to go from 1 mole to 2.5 mole, what do? I multiply by 2.5. Or let's just do it the classical way. MnO4 minus here, and then nitrite ions here. This is 1 mole, this is 2.5 moles. I know MnO4 minus the moles which had reacted, 6.07 times 10 power minus 3. So how much would this be? X would be 6.07 times 10 power minus 3 multiplied by 2.5, which would become 0.015175 mole. Is this the answer? No. This is a long question. Now, what do I have to do now? I know the moles of nitrite ions, correct? Can I find the concentration of nitrite ions in X? Yes, I can. C is equal to 1000 N divided by V. 1000 multiplied by the moles of nitrite ions in X, which is 0.015175 divided by the volume of X initially, which was 250. There we go. What is my answer? 0.0607. 0.0607 is my answer. Now, some of you might be thinking, wait, this is the concentration of nitrite ions. But the question asks is for the concentration of sodium nitrite. Well, it's the same thing. Why is that? When I write NaNO2, this becomes Na plus NO2 minus. It's 1-to-1 stoichiometric ratio for sodium nitrite and nitrate. Whatever the concentration of this is the concentration of this. Simple enough. Right. The next question is table 2.1 shows some electrode potential. This question is from electrochemistry from some electrode reactions involving manganese compounds. All right, interesting. Aqueous manganate ions, MnO4 2 minus ions, are unstable in acidic conditions and they undergo a disproportionation reaction. What is a disproportionation reaction? It is when the same species is oxidized and reduced as well. Disproportionation reaction is when the same species is oxidized and reduced. Okay. E naught of cell, which is E naught of reduction minus E naught of oxidation, is plus 1.14 volts. Now, construct an overall ionic equation for this disproportionation reaction. We know three things. First thing we know is this, the E naught of cell. So what I can think of is we can simply choose two reactions. And then when we minus both of them, if the answer is plus 1.14, those are your two reactions. But only I can repeat this method. Take two reactions. Example, randomly I take this and this. Minus 2 of both of these reactions because it's E naught of reduction minus E naught of oxidation. So whichever reaction involves manganate ions being reduced minus whichever reaction involves it being oxidized. And you get plus 1.14. Those are your two reactions. You cancel them out, you write the ionic equation. But this is fluke. You only use this when you don't have time. Let's do this the classical method using our own knowledge. I know the E naught of cell. I know that we are talking about aqueous manganate ions, which is MnO4 2 minus. And the most important thing, it's a disproportionation reaction, meaning understand what we are looking for. We are looking for two reactions. First point. Second point, in both reactions, MnO4 2 minus will be reduced, and in the other reaction, MnO4 2 minus will be oxidized. Now, reduction and oxidation are two opposite reactions. What does that mean? If I go from here to here, this is gaining of electron, this is reduction. But if I go backwards, this is oxidation. What am I trying to explain? I'll repeat. If I go from left to right, this becomes reduction. But if I go from right to left, it becomes oxidation. In this case, I will have two manganate ions in two different reactions present diagonally to each other. Why diagonal? In one case, the reaction will go from left to right. In the other case, the reaction will go from right to left. So both of them need to be diagonally present in two different reactions for it to become a disproportionation reaction. Okay, let's look for two reactions which have manganate ions and present on opposite sides. Which are these two reactions? And the fourth point, I just noticed, it's acidic conditions, which means that H plus ions will also be present. Right. So what I can look for is I can maybe go with this. It's just trial and error by this point. I can go with this. Why am I going for this? This involves reduction. I am gaining electrons. I have manganate ions, I have H plus ions. Now, what do I need to do next? Choose another reaction wherein MnO4 minus is present somewhere here so that oxidation can take place. Right. MnO4 2 minus, the only place it is present is here. Therefore, I go with this. Now, we need to understand this. If I have two electrode reactions and both of them have a positive E naught value, then the value which is less positive is considered as negative. I repeat, let's say I had plus 1.7 in this. It would have been really, really simple. This would be reduction and this would be oxidation because a negative E naught value means electrons are being oxidized. Sorry, electrons are being lost, which means that it is a more reactive metal, which means oxidation is taking place. And a positive E naught, right, you could remember it like this. This is, I'm just telling you a way of remembering it. Let's say I have Na plus. Now, if Na plus wants to go to its neutral state, it goes to Na. What does it do? It gains an electron. So you could remember positive E naught value, gaining of electron, reduction. Similarly, if I have, let's say, a chloride ion, it goes to a chlorine atom. What does it do to go to its neutral state? It loses an electron. So negative E naught value, lose electron, oxidation. Therefore, if it was this and this, it would be really clear. This is reduction, this is oxidation. But both values are positive in this case. What do I do now? The lower positive value is considered as the negative value, the value which undergoes oxidation, or the electrode which undergoes oxidation. Now, I know these are two of my reactions. I write both of these reactions here first. MnO4 2 minus plus 4H plus 2E minus becomes MnO2 plus 2H2O. And for the oxidation reaction, which is this one, I just flip it. Always remember, the oxidation reaction will involve the loss of electrons and a negative E naught value, or in this case, a less positive E naught value. And whenever we find it, and we are writing the overall equation, we always flip the oxidation reaction. So this becomes MnO4. We keep the reduction as it is, but we flip the oxidation reaction. MnO4 2 minus becomes MnO4 minus plus E minus. Now, whatever is on the left hand side, we write it together. I have two MnO4 minus. In fact, I wait. Now, we always flip the oxidation reaction. Now, what we have to do now is we need to balance both these equations. The way we balance it, we look at the number of electrons. Two electrons here and one electron here, which means that we multiply this equation by 2. Now what we do is we cancel the electrons. This electron was on the left side, two of them. Two electrons are on the right side, they get cancelled. Furthermore, is there anything else that can get cancelled? Nope, nothing else. It's always the electrons only that get cancelled. Now, 3MnO4 minus 3MnO4 2 minus, in fact, which is this, plus 4H plus gives 2MnO4 minus plus MnO2 plus 2H2. This is, I can just make this smaller, and now I can place this equation right here. Simple. Now, this is an interesting question. Suggest and explain how the A naught of cell value of the disproportionation reaction, which is listed above, changes with an increase in pH. You need to understand what happens when the pH increases. Let's say pH goes from 3 to 8, which means that the acidity decreases, correct? Which means that H plus ions decrease. Now, in two of these reactions, H plus ions was only being used here. If H plus ions decrease, the equilibrium, it's a reversible reaction. So what happens? The equilibrium shifts to the left-hand side. If the equilibrium shifts to the left-hand side, which reaction takes place more now? Oxidation takes place more, which means a negative E naught value, which means that this E naught value becomes more negative. I'll repeat, pH increases. Let's just write this down. pH increases. What happens now? H plus ions decreases. What happens now? In this second reaction, the equilibrium shifts to the left-hand side. So how does that affect me? Oxidation rate increases. And what is oxidation linked to? A negative E naught value. If the rate of oxidation increases, the E naught value becomes more negative or less positive. It's the same thing. So the 1.7 value becomes, let's say, this second example becomes 1.4. Now, when I minus both of these values, nothing happens to this because there was no hydrogen ions here. When I do 1.4 minus 0.56, what does the value become? It becomes smaller than plus 1.14, which means that the E naught value decreases. So E naught of cell value. The E cell value decreases since when the pH increases, the H plus ion concentration decreases. Why am I writing it in square brackets? Square brackets indicate the concentration in mole per dm. So pH increase, concentration of H plus ion decrease, as a result of which the equilibrium shifts to the left-hand side. The value of E reduction decreases. Obviously, this was the one being reduced. It had a more positive E naught value. This value became more negative or less positive. And that is what I've written here. The value of E reduction decreases, which means that E cell value overall decreases. And why did the E reduction decrease? Because the equilibrium shifted to the left-hand side. Why did the equilibrium shift to the left-hand side? Because H plus ion concentration decreased. And why did it decrease? Because the question said that the pH increased. Right, so the next question asks us that carbon disulfide is flammable and it reacts readily with oxygen as reaction 1 shows us. Table 1 3.1 shows the standard enthalpy of formation, okay, and the standard entropy for some substances, calcium sulfide, oxygen, carbon dioxide, and sulfur dioxide. What is the question? The question is asking to calculate the standard Gibbs free energy change in kilojoule per mole for reaction 1 at 25 degrees Celsius. In order to do this, you should know the Gibbs free energy change formula. The standard Gibbs free energy change formula, which is taught to most students, is delta H minus T dot delta S. While this is correct, I teach a different method to my students, which makes it very, very simple to do 95% of Gibbs free energy change questions. Because the thing is, the question always asks to write the answer in kilojoule per mole, which means that you need to divide by 1000. And secondly, students sometimes get confused with this negative sign. So what I teach them is gives free energy changes delta H minus T dot delta H divided by 1000 and add a bracket sign next to it. So that why you can differentiate between the negative sign and the bracket. This will make sense in just a moment. The Gibbs free energy change is the enthalpy change of formation. Now, do we have the enthalpy change of formation? No, we need to calculate it in this reaction. So what we can do is we can make a Hess cycle. Let's quickly make a Hess cycle here. For the enthalpy change of formation, the way we make a Hess cycle is here we write down the reaction, and here we write down the reactants, and we point the arrow upwards as we have done in AS level. So I just write the entire reaction here. CS2 gas plus 3O2 gas makes CO2 gas plus 2SO2 gas. Now, when talking about reactants, I would write carbon here plus sulfur, which exists as S8 in its molecular form, plus oxygen. Now I need to balance them out. How many oxygens are, this is a balanced equation, but how many oxygens are needed itself? 6 oxygens are needed. So I'll write 3 here. 2 sulfurs are needed, so I can write 1/4 here, and 1 carbon is needed, so I leave it as it is. Now I point the arrow upwards. This is the enthalpy change of formation. Thankfully, in kilojoule per mole for CH2 is 116.7. For oxygen, since it's an element, it's 0. For CO2 is minus 393.5. And for SO2 is minus 296.8. Now, so the way this works is I make an arrow, and if both arrows, which two arrows am I talking about? This arrow and this arrow. If both of these point in the same direction, I use the same sign. If in any case they point in the opposite direction, for example, here it points this way, but here it points this way, I just add a negative sign. So this becomes minus 116.7 minus 393.5. This is not the minus which I have added, it's already present. And now because this is 2 moles of sulfur dioxide, I multiply minus 296.8 with 2, which gives me the answer of minus 1103.8 kilojoule per mole. Now, since I found out the enthalpy change of formation, all that is left for me is to find the entropy change. Now, the way I calculate the entropy change is simply the entropy of products minus the entropy of reactants. This formula is listed in your syllabus too. So, what is the entropy of the products? 213.8 plus 248.2 multiplied by 2. This is one bracket, and this is the overall bracket for the entropy of products minus the entropy of reactants. What is it? It is 205.2 multiplied by 3 plus 237.8. What does that give me? This gives me an overall answer of minus 143.2. And now I have the entropy change. I just simply multiplied by 298. What is 298? It's the temperature in Kelvin. The temperature always needs to be in Kelvin. Since this is 25 degrees Celsius, the temperature in Kelvin is the temperature in degrees Celsius plus 273. This becomes 298. And now I just simply divide it by 1000. What does that make? This gives my answer of minus 42.6736. But this is not my answer. I have to complete the equation. Minus 1103.8 minus 42.6736. Why did I add two minus signs? Let's understand this. This minus sign is this one. This minus sign is this one. Therefore, minus minus becomes plus, which gives me the answer of minus 1061.1 kilojoule per mole. This is my answer. Minus 1061.1 kilojoule per mole. The next question is carbon disulfide reacts with chlorine to form tetrachloromethane as shown in reaction 2. Calculate the maximum temperature in Kelvin for reaction 2 to be feasible. Now, when we talk about the feasibility of a reaction, and we are also talking about the Gibbs free energy change, there is only one rule which we have to keep in mind. The Gibbs free energy change needs to be negative. Simple, simple. I repeat, if a reaction has to be feasible, which means that a reaction will occur spontaneously, the Gibbs free energy change will be negative. But in this case, however, for simplicity of the reaction, yes, I repeat, for the simplicity of the equation, I will assume that for the reaction to be feasible, the Gibbs free energy change should be zero. Now, it's not necessary that you take zero, but this is most of the time mentioned in the marking scheme to just take zero. But if you take negative, not a problem at all because it makes sense and it is correct. Feasibility means Gibbs free is negative. Therefore, if you take Gibbs free as negative and you treat the equation like an inequality, that's also fine. But again, for the simplicity in this case, I take the Gibbs free energy change to be equal to zero. Gibbs free energy change is delta H minus T dot delta S divided by 1000. The dot is the multiplication sign. Hence, minus delta H would become minus T dot delta S divided by 1000. The minus sign gets cut. Delta H becomes multiplied by 1000, which becomes minus 261.6. Yeah, or instead 261.6 times 1000. And the Gibbs free energy change comes in the denominator, divided by minus 365.5, which equals to the temperature. This temperature is already going to be in Kelvin, which is 715.7 Kelvin. We mostly write in three significant figures since our raw data is in three significant figures. Which means that the lowest value is in three significant figures. Now you might be thinking this is in four. Well, you can write in four, but you can write one less than that too. It's fine. So the answer comes out to be 715.7 Kelvin, which makes it to 716 Kelvin. We mostly write our answers in three significant figures. We can write the entire thing as well, since our raw data is already in four significant figures. In fact, that would be a better option to write 715.7 Kelvin. The next question is from transition elements, which states, why do transition elements have variable oxidation states? Now we need to understand this. When we talk about transition elements, we talk about the D subshell. The reason they have variable oxidation state is that sometimes Fe becomes plus 2. Fe also sometimes become plus 3. Why is that? It's because we need to understand how electrons are lost from transition elements. You should know this by now that electrons are lost from the highest shell or the shell with the highest energy. Let's take an example of Fe. When I talk about Fe, the atomic configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1, 2, 3, 4, 5, 6. 3d6, 4s2, and 3d6 are those two things which we need to focus on. 4s2 and 3d6. Now, sometimes what happens is two electrons are lost from 4s2 because it is the highest energy cell subshell. So this becomes Fe2 plus. But sometimes an electron is also lost from 3d6. So this becomes 3d5, and this is already lost as well. So this becomes Fe3 plus ion. I repeat, Sometimes two electrons are lost from 4s2 since it is the highest energy subshell. This makes an Fe2 plus ion. But sometimes not only are the two electrons lost from the 4s subshell, but also one electron from the 3d subshell, which makes it 3d5 and an Fe3 plus ion is formed. This is the meaning of variable oxidation states. But how is it possible that sometimes two electrons are lost and sometimes three electrons are lost? This is what the question is asking. It is possible. Why? Because the 3D and the 4s subshell have very similar energies. Therefore, if you give a particular amount of energy to lose an electron from the 4s subshell, sometimes an electron is lost from the 3D subshell also because both of them have similar energy. So we will say that this is because the 3D and 4s subshell have similar energies. Right. The next question asks us to sketch the shape of a 3D Z2 orbital in figure 4.1. 3D orbitals are of a few types. There is Z square, there is X square, Y square, then there is DZ square, DX square, Y square, there is DXY, then there is DYZ, and there is DXZ. These are the five d orbitals that are present. When it's asking us to draw 3D z square, it simply means to draw a dumbbell on the z line and draw an oval shape around the dumbbell, just like this, and we're done. Next, samples of Cu2 plus are reacted separately with an excess of solution A. Okay, one second. Why did I call this Cu2 plus? The reason I called this Cu2 plus is a copper ion, as we talked about in one of the earlier questions, a copper ion or any ion, metal ion is always surrounded by six water molecules. This is one, this is two, this is three, so on and so forth, four, five, and six. Each of these water molecules has an oxygen atom which has a lone pair, and an ion dipole force is formed between the lone pair and the vacant d orbital of the metal ion. An ion dipole force is formed between the lone pair and the vacant d orbital or the vacant subshell of the metal ion. Therefore, because six water molecules are surrounding it, therefore it's called CuH2O6 2 plus, making it a complex ion. I can also write this as Cu2 plus aqueous. This is exactly correct. And this is the exact same version, but in a different form. It's the same thing. It reacted with an excess of solution A and with an excess of solution B. You already would have learned there are simply a few reactions. There is some with limited reagents and there is some with excess of solutions. It's just four to five reactions of copper, which we need to learn by heart. So the reaction of Cu2 plus aqueous with solution A, which is excess, is a precipitation reaction. You should have this on your fingertips that this is the reaction of aqueous sodium hydroxide with Cu2 plus aqueous. So I already know this is NaOH. Now the reaction of this with solution B is a ligand substitution reaction. Now simply this is simple. This is aqueous ammonia, excess of aqueous ammonia. You could also write this as excess of concentrated hydrochloric acid. It's the same thing. So, suggest a possible identity for solution A and for solution B. Okay. What are the observations when Cu2 plus aqueous reacts with an excess of aqueous sodium hydroxide? A pale blue precipitate is formed. These are things which you need to remember and do not require any such scientific explanation. It's simple things that we need to remember in order to answer. What is the formula of the copper containing product? You could write it as CuOH twice, or I like to write it as, in either cases, it's both correct, but This would be a better version, in my opinion. It's a longer version, but it makes sure that the concepts are clear. What happens is the oxygen atom, the lone pair on the oxygen atom, attracts two hydrogens towards itself, making two water molecules. This process makes sure that the concept is clear. What happens here? When I have aqueous sodium hydroxide, I have hydroxide ions, which means that it's OH minus ions. Now, what happens here is I have CuH2O6, which means that copper, and surrounded by six water molecules. What happens here is that because I have two hydroxide ions, which have a lone pair and a minus one charge, two hydroxide ions take away one hydrogen atom from one water molecule. I have a copper ion here, I have two water molecules here, and I have two hydroxide ions here. Each of these hydroxide ions, using its lone pair of electron, attracts a hydrogen atom to form a dative bond. What does that make? The Cu was attached to six water molecules. Now, from two of these water molecules, a hydrogen is born, which means that it is CuH2O4 and OH twice. It's not that the two hydroxide has replaced the two water. No. In that case, it would have been a ligand substitute reaction. It is a precipitation reaction because only the hydrogen is gone. The whole thing has not replaced the water molecule. But in the case of NH3, it is a complete ligand substitution reaction, and that is why a solution is formed. A deep blue solution is formed. Now, always remember, whenever the formula has a charge of zero, it has no charge here, so it is assumed as zero. It's always a precipitate. Since it was zero, it's a precipitate. Now it's a solution here. Now I can bet this will have a charge on it, and it obviously does, since this is CuNH3 4 H2O twice 2 plus. Since NH3 has no charge, Cu has a 2 plus charge, and water has no charge, so the overall charge becomes 2 plus. Now the next Right. So the next question talks about a solution and it asks us as to explain as to why this particular complex is colorless. Before understanding why this complex containing the silver ion is colorless, we need to understand as to how color appears in a transition metal complex. Let's take an example. I will be taking the nickel complex, and this is only to show you guys as to how does color appear in a complex. I'm taking a random couplings in a random metal ion. This would be nickel NH3 twice. And in this case, since it's nickel is a transition metal ion, it has variable oxidation states. It could have the oxidation state of +3, +1, +2. In this case, I would be taking as +1. Now, if we look at the periodic table and see the electronic configuration of nickel, what would it be? It would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8. 3d8. Now, you might be thinking, why not shift an electron from the 4s orbital into the 3d orbital like we did in copper and in the case of chromium? We would only do that if the d subshell was going to be stabilized. Now, let's understand this first. When does the D subshell become stable and when does the D subshell become unstable? The D subshell only becomes stable if it is half filled or fully filled. Half filled meaning 3D5, fully filled meaning 3D10. If the D subshell 3D, 4D, 5D, 6D, whatever, if it has 5 electrons, it is half filled, it is stable. If it has 10 electrons, it is fully filled, it is stable. If it is anything other than 5 and 10, which is 1, 2, 3, 4, 6, 7, 8, and 9, all of this would mean that the D subshell is incompletely filled, which means it is unstable. Now, second point. The only time an electron will jump from a 4s to a 3d orbital or from a 5s to a 4d orbital will only be if the jumping makes the d subshell stable. If it jumps, this becomes 3d9. This is not stable. And it also makes it 4s1, which also makes it unstable. So right now we have this to be stable and this is unstable. If I make the electron to jump, both of them become unstable. And this would never happen. This is why this stays as it is. Now in this case, the D subshell is incompletely filled. What happens is ammonia, the nitrogen atom has a lone pair of electron. This lone pair of electron undergoes repulsion with the electrons present in the incomplete d subshell of the nickel ion. I repeat, the lone pair of electrons on the nitrogen atom in ammonia undergo pair of electron on the nitrogen atom in ammonia undergo repulsion. With they undergo repulsion with what? They undergo repulsion with the electrons present in the D subshell of the nickel ion. It makes sense still here? Now what happens? Because of this repulsion, this 3d8 orbital undergoes splitting. And this process is completely known as d splitting. So this is the first process that happens here. Now what happens? The d orbitals split into two parts. This process is called d splitting. We all know the five d orbitals that are present. This orbital is dx squares dash y square. Now it's not necessary that the first orbital should be dx square dash y square. I'm just labeling it randomly. This is dz square. This is dxy. This is dyz, this is dxz, and then when it undergoes splitting, now it depends. If this was an octahedral complex, which would have been formed, then the splitting would be different. If this would have been a tetrahedral complex, which would have been formed, then the splitting would also have been different. But that is the concept of d splitting, which we don't need to understand in this question. We just need to know that splitting takes place. Let's say this type of splitting takes place. Dx square dash y square and dz square. This becomes dxy, dyz, and dxz. Now, there is two electrons, 2, 4, 6, 7, and 8. We have an empty d subshell here. And what happens is electrons which are present in the d subshell which have a lower energy, the ones which are present on the lower side or ones which are present at the bottom, those d subshells have a lower energy and these d subshells have a higher energy. And the energy between them is called delta E. This is the energy gap. Now, electrons in the d subshell which have a lower energy want to move to the d subshell which have a higher energy. They want to jump to another d orbital. Which d orbital? The d orbital which has a higher energy. Now, in order to jump, it needs to gain energy, which is equivalent to what? It should be equivalent to delta E, which means that these electrons needs to gain some energy from somewhere. We don't know right now from where. The energy which they gain should be equal to delta E in order for them to jump from a lower energy orbital to a higher energy orbital. The point is, where does this energy come from? This energy comes from particular wavelengths of light. And this is where the concept of transition metal complexes having colors come from. Now, let's understand this. Different complexes have different delta E values, correct? Different complexes have different delta E values, and your syllabus also makes you understand why does the different delta E values comes from. These two factors, the nature of the ligand and the nature of the transition metal ion, don't need to know that. For now, just understand different complexes have different delta E values, which means that electrons, if they need to jump from a lower to higher energy orbital, they need to absorb different amounts of energy each time. First point, in different complexes, electrons need to absorb different amounts of energy each time. Now, they need to absorb different amounts of energy in different complexes, but every single time, whatever the amount of energy they absorb, it will always be equivalent to delta E. Right, this is clear. Now, how does, for example, if I have complex A and I have complex B, both of these have different delta E values. Now, electrons need to absorb energy equivalent to their delta E values. But how do electrons get different energies to be able to absorb them? For example, if complex A, let's take an example, requires 20 joules of energy and complex B requires 40 joules of energy, the electrons in complex A and B require 20 and 40 joules of energy respectively. Where do they get the 20 and 40 joules of energy from? They get them from absorbing particular wavelengths of light. For example, one complex will absorb red light, the other complex will absorb blue light. One complex will absorb green light, the other complex will absorb yellow light. Now, there is a particular wheel, a color wheel, which you need to understand, or how a color wheel essentially looks like. So, the way the color wheel works is that if a electron absorbs yellow light, then it will reflect all of the lights other than yellow light, which is this color, this, and this color. The mixture of all these colors will be the opposite of the light which it absorbed. I'll repeat. Let's say electron absorbed this light. So which light should it reflect? It would reflect this light. You know how? This, and this. The mixture of all of these colors will be equivalent to this color or whatever is the opposite of this particular color. So, if an electron absorbs green light, it will reflect red light or orange light, whatever is the opposite of this light. Similarly, this is the thing which we see in plants. If the chlorophyll is, people who take biology A level will understand this. Chlorophyll A and chlorophyll B absorb light present in the violet and the blue regions. Since they absorb energies since they absorb light in the violet region, this is why they reflect green color. And this is why chlorophyll A and B appear to be green in color. This is how it works. Now, the reason why it is colorless is because it is not absorbing light. If a particular complex it's not absorbing any light, then it will not reflect any light, or it will reflect all of the light, and the mixture of all of this light is white. It means the same thing. So let's take the first example. A complex is absorbing a particular light. So what will happen? Let's say it's absorbing this light. So which light will it reflect? It will reflect the light of the opposite color, which is this one. Now, what if a complex is not absorbing any light? It is allowing all of these lights to pass through, and the mixture of all of this light is white, which we also call colorless. Now, we understood that this particular complex is not absorbing any light, and we need to write this down. But the thing is, why is it not absorbing any light? Because why was light needed to be absorbed in the first place? To allow the d orbitals to be promoted, to allow d-d transition to take place. That is the correct terminology. This jumping of electrons is called d-d transition, which I'll write in the answer. So light was needed to be absorbed in order to allow DD transition to take place. But why does not DD transition take place in the case of silver? Because it has a 3d10 orbital, or instead it has a 4d10 orbital. This is why a silver metal ion containing complex is colorless, because it has a filled d orbital. So after DD splitting takes place, a pair of electrons will also be here. So how can the electron jump? There is no space. So our reasoning would be the d orbitals are filled, as a result of which no DD transition take place. Simple. The main purpose of explaining this entire thing was to show the concept of colors. And the question comes in many, many different ways. This question was particularly simple on how the complex is colorless. Thus, some difficult questions also say, how do transition metal complexes get the colors from? So this is where we have to explain all of this. That DD splitting occurs when repulsion occurs between the transition metal ion electrons present in their d subshell and the lone pair of electrons present in the ligands, which are attracted to the transition metal ions. Because of this repulsion, DD splitting takes place. And now, after DD splitting takes place, DD transition takes place. And in order to allow for DD transition to take place, electrons need to be promoted to a higher energy orbital, as a result of which light is to be absorbed, and then the complementary color is reflected. I'll repeat again for another question, which regularly asks us about how do transition metal complexes gain color. So the reason is, firstly, I'll just write it in short. Repulsion occurs. Now we know between what? Between the lone pair of electron of the ligand and the electrons present in the d subshell of the transition metal ion. Now, when repulsion occurs, d splitting occurs. After DD splitting occurs, DD transition needs to occur. In order to allow for DD transition to occur, light of specific energies and wavelengths needs to be absorbed, which have energies that are equivalent to the delta E value. Once that light is absorbed, DD transition takes place and the complementary color is reflected. And this is the color which we see of the transition metal complex. Right now, it's a very simple question. Why the complex is colorless? Obviously, because the D subshell is completely filled. Obviously, it makes sense, right? Why do transition metal complexes have color? Because they absorb light. So why do not have color? Because they don't absorb light. Why don't they absorb light? Because the D subshell is completely filled. So the D subshell is completely filled. Now it might think that I'm repeating again and again, but it's just so that you could remember it for a longer amount of time. The D subshell is completely filled, so the DD transition does not take place. Simple as that. No need to write about the delta E values because there is no light that is absorbed. So there's no need for that. Now, two bidentate ligands. Now, there are different types of ligand which you should know. One is monodentate ligands, one is bidentate ligands, one is tridentate ligands, and one is polydentate ligands. Ligands have the same meaning. They have lone pair of electrons and they form dative covalent bond with the d orbitals, the empty d orbitals of the transition metal ion. But what makes all of these ligands different? They have different amounts of lone pair of electrons and they form different number of dative bonds with the transition metal ion. So let's say we have a monodentate ligand, one lone pair of electron forms one dative bond with the transition metal ion per ligand. Let's say I have this AgNH3 twice plus. This means I would have an Ag here. I would have a ammonia molecule here and an ammonia molecule here. Since this is a linear complex, a linear complex is a complex having two lone pair of electrons, having two dative bonds. And two dative bonds, two ligands, what does that mean? It means both of these are monodentate ligands. Each ligand forms one dative bond. In the case of bidentate ligands, as we see here, one nitrogen here, one nitrogen here. Each nitrogen has a lone pair of electron. So one En molecule forms two bonds. One DPYS molecule forms two bonds. So what is it asking? Explain what is meant by a bidentate ligand. This is for 2 marks. We need to write two things. We need to write it is a species with two lone pair of electrons. And because it has two lone pair of electrons, it forms two dative bonds with central metal ion. The next thing is about ruthenium ions, Ru3 plus. Okay, they form an octahedral complex. RuDp, we just saw DPYS right here, and we know it's a bidentate ligand. Okay, so we have two bidentate ligands here. What does that mean? That means we already know that four dative bonds are right here. Two chlorine molecules. Now you need to remember this. Chlorine is a monodentate ligand. Water is a monodentate ligand. Hydroxide is a monodentate ligand. And then we also have En. En is a bidentate ligand. Uh, this one, DPYS, is also a bidentate ligand, but this is not in the syllabus. This is something which they have given themselves. Right. So we know this is a monodentate ligand, and we have two monodentate ligands, so two dative bonds, total six dative bonds. This is why it's an octahedral complex. With the ligands DPYS and chloride ions, this complex, I'm just going a bit fast. You could rewind it and see, there's no problem with that. This complex shows the same kind of stereoisomerism as RuNH3 4 Cl2, but also shows a different type of stereoisomerism. We need to understand this, that there is no bidentate ligand here. Pl2 monodentate, 2 monodentate, and NH3 four times. Again, four monodentate. So we have six monodentate ligands forming six dative bonds. Now, why am I saying this? There are two kinds of stereoisomerism. The first type of stereoisomerism is geometrical isomerism. And the other kind of stereoisomerism is optical isomerism. Optical isomerism will only occur if you have a minimum of two bidentate ligands. I repeat, optical isomerism will only occur if we have a minimum of two bidentate ligands. We have zero bidentate ligands here. What does that mean? That geometrical isomerism is occurring in this complex. Now, what does the question say? This particular complex, this one, shows the same kind of stereoisomerism as in this, aka geometrical isomerism, but also shows a different types of stereoisomerism. What is this? This is optical isomerism. Complete the three-dimensional diagrams in figure 4.3 to show the three different stereoisomers of this particular complex. The DPYS ligand can be represented using this. So what we can do here is we could make a cis, because geometrical isomers are two, right? There is cis and then there is trans. We could make a cis isomer. We could make the mirror image of the cis isomer. So the second isomer becomes optical. I'll show what I am trying to explain. Firstly, whenever it says octahedral complex, right? And then it also says three-dimensional diagrams. First thing you should do, make the 3D structure. How do you make the 3D structure? Two straight lines, which they have already given, two wedges on the bottom right and the bottom left, and two lines on the top left and top right going like this. Make this the standard, and so that you don't have to think about it every single time you make this if they ask about an octahedral complex. Two wedges again, and then two lines going away from you, and the wedges are coming towards you. Right. Now, what I was saying is we could make a cis isomer so that the isomer one would become geometrical isomer, and then we would make the mirror image. So isomer 2 would become an optical isomer. For isomer 3, we could make a trans isomer that works as well. Or you could also do this. You could make a trans isomer, you could make a mirror image of a trans isomer, and then you could make a cis. Even that works. but I choose to make the mirror image of the cis since it's much more easier to do that. I'll put a Cl and a Cl here, and I can represent the DPYS ligand using this. So that's what I'll do right now. I'll put an N on this and this bond, and then this is how I would draw it essentially. Like this, and this. And now I would make the mirror image. When you make the mirror image, understand this. What will be your line of symmetry? Your line of symmetry is never y is equal to 0. What do I mean? Let's take an example. This is y is equal to 0. This is x is equal to 0 for those who have a basic understanding of graphs. When I say y is equal to 0 of the line of symmetry, if I draw something here, it gets translated here. When I say x is equal to 0 is the line of symmetry, when I draw something here, it gets translated here. So whenever I say mirror image, x is equal to 0 is the line of symmetry, which means like this. So now the things which are at the top and the bottom remain the same. It's just the things which are on the left come on the right, and on the right come on the left. CL was on the right, CL comes on the left. This part stays as it is. This was on the right, it comes on the left. The whole thing was on the left, it comes on the right. Simple as that. This becomes a trans isomer. A trans isomer means that identical bonds or identical ligands are on the opposite sides. Ligands would be a better word, meaning N, the dBys ligand would be here, and another dBys ligand would be 180 degrees to it. The Cl and Cl would also be placed 180 degrees. So the different types of stereoisomerism shown, we already wrote that, geometrical, optical. Now, deduce which stereoisomers are nonpolar. This is an AS question. Trans isomers are always nonpolar. Why is that? Because the dipoles are on opposite sides, exactly 180 degrees. If I were to make a sketch of the dipoles here, it would be this one, N going upwards, nitrogen going downwards, since the nitrogen is pulling the electrons of the ruthenium. This is going upwards, this is going downwards, downwards, upwards, upwards, and upwards. Meaning it would be something like this. Every single up one is canceling the down one. This cancels this cancels this. So while the entire isomer would have many dipole moments, the net dipole moment will be zero. And this is always, always the case in trans isomers. And this is what we learned in AS. Trans isomers are nonpolar because the net dipole moment is zero. So which is nonpolar? Isomer number three. Why isomer number three? Isomer number three because it's a trans isomer. And why are trans isomers non-polar? Since individual dipole moments cancel out, you can either write that individual dipole moments cancel out, or you could write that the net dipole moment is zero. When the net dipole moment of a molecule is zero, automatically it's a non-polar molecule. Next question is from reaction kinetics. This should be very, very easy. Nitrosyl chloride NOCl can be formed by the reaction between nitrogen monoxide and chlorine. Always highlight the main points so that when you read the question, you only read the highlighted parts. Now, the initial rate, okay, it's talking about the initial rate of the reaction is investigated starting with different concentrations of NO and Cl2. The results obtained are shown in table 5.1. This is the reaction which occurs. We have three experiments, and in each of the experiments, they are just tweaking with the concentration of the one of the reactants, which means that here Cl2 is same, but NO becomes different. So the rate of reaction becomes different. Okay. Use the data in table 5.1 to deduce the rate equation for this reaction. Now, if we need to understand the rate equation for this reaction, we need to first find out the individual orders of reaction with respect to each of the reactants. So let's do that. Now, when I talk about the order of reaction with respect to the concentration of nitrogen monoxide, I repeat, when I need to find out the order of reaction with respect to the concentration of nitrogen monoxide, I need to take two experiments wherein the concentration of nitrogen monoxides changes, but the concentration of chlorine stays the same. This is experiment one and two. So I will write for order of reaction with respect to, please write in full in the exam, concentration, the square brackets indicate concentration in mole per dm cube. This is why there's a square bracket here too. I need to write this, that experiment one and two are selected, since we need to make it easier for the examiner to understand as to what we are talking about. Right. Now, I'll write three things. What is the change in concentration? What is the rate? And then eventually, what is the order of reaction? So, I will write what is the change in concentration. Let's take experiment 2 divided by experiment 1. I could also do experiment 1 divided by experiment 2, but the answer would become smaller or less than 0. I'll take bigger number divided by smaller number. So let's take experiment 2 divided by experiment 1. This would become, hence why the arrow is a bit wrong. It would be like this. Yes. So experiment 2 divided by experiment 1, 0.075 divided by 0.025 would give 3 times, which means that the concentration has decreased 3 times when going from experiment 2 to experiment 1. So I'll write times 3 here. Now, you might be thinking I said decreased 3 times, but I'm writing the concentration as times 3 is the same thing. If I divide by 3, I go from 2 to 1. If I multiply by 3, I go from 1 to 2. It's the exact same thing. I could also write 1 over 3, but then everything would have to become the reciprocal. I'm not doing the whole thing being reciprocal. What happens to the rate? 3.32 times 10 power minus 1 divided by 3.68 times 10 power minus 2. The rate decreases 9 times or increases 9 times when I'm going from experiment 1 to experiment 2. Now, you should know this by now if you have learned the syllabus. Concentration becomes 3 times, rate goes down 9 times, which means that the rate changes according to the square of the change in concentration. The rate changes according to the square of the concentration, which means that it is a second order reaction. If the rate would have decreased times 3, first order. If the rate would not have changed, zero order. But because it has changed according to the square of the concentration, this is second order. So first thing is here, second thing is here, the third thing is, hence order of reaction, not the overall order of reaction, the order of reaction with respect to the concentration of nitrogen monoxide is 2. This is the first mark. Next mark, for order of reaction with respect to the concentration of Cl2. Experiment 1 and 3 are selected. Now, let's see why did I select experiment 1 and 3. I should have essentially selected the two experiments wherein the concentration of Cl2 changes and the concentration of NO does not change. But do we have any two experiments where the concentration of NO does not change? In all three cases, it's different. So now, what I can do is, I know what the change in the rate of reaction is when NO takes a part in it. I repeat, I know what the change is in the rate of reaction only if nitrogen monoxide affects it. Because in experiment 1 to 2, Cl2 was same. Meaning, just because NO changed, this is why the rate of reaction changed. So now I know what effect there is on the rate of reaction just because of NO. When I go from experiment 1 to 3, the concentration of Cl2 changes, but the concentration of NO also changes. Meaning the effect on the rate of reaction is not only because of Cl2, but also because of NO. But I already know what effect there is because of NO, meaning I can just cancel out that effect or I can cut down the effect and then eventually find out what is the effect on the rate of reaction because of Cl2. Because the purpose of keeping one reactant constant and what changing one reactant was to see what effect would there be on the rate of reaction because of a particular reactant. We don't have that freedom here. Both things are changing in every single experiment. As a result of which, now we need to cut down the effect of NO on the rate of reaction to find out only the effect of Cl2 on the rate of reaction. Now, how do we do this cutting down of the effect? The way we do this is that I know that 0.05 divided by 0.025, which is this and this, is simply 2, meaning the concentration of nitrogen monoxide has increased 2 times. And I know what the rate of order of reaction is in with respect to NO, which is that if NO increases 2 times, rate of reaction will increase 4 times. So I will go from 3.68 times 10 power minus 2 multiplied by 4. Let me just do that right here. 3.68 times 10 power minus 2 multiplied by 4. That makes it 0.1472. So now the rate of reaction was first 3.68 times 10 power minus 2, and now we brought it to 0.1472. Why did it come up to this? It was because of NO. But now we're still not completed with the journey. The journey is until 5.89 times 10 power minus 1. So who is responsible for this? Cl2 is responsible for this. Now we do 0.06 divided by 0.015. 0.06 divided by 0.015 would be 4 times. I'll write here the change in the concentration of NO is 2 times. So the rate of reaction would be times 4, meaning 3.68 times 10 power minus 2 times 4 would be 0.1472. Now, next, the change in the concentration of Cl2 is 4 times. And now, when I go from 5.89 times 10 power minus 1 divided by 0.1472, 5.89 times 10 power minus 1 divided by 0.1472, it becomes 4.00, which is approximately 4 times. You see here, times 4 times 4. What does that mean? It means first order reaction with respect to the concentration of chlorine. Now we know the individual orders of reaction, and now we can find the overall orders of reaction. So now the overall orders of reaction, or not even the overall order of reaction, the rate equation. The rate would be K, the rate constant, and O, second order, and then Cl2, first order. Now, I could have done this in a simpler way, which was simply saying that let's do the simpler way as well. This was the longer way, agreed. And why was I doing this the longer way? In order to make sure that the concept is fully understood. The way I could have done this is said that, okay, I know the concentration, I know the order of reaction with respect to NO. The first step would be the same in both cases, which is second order. This would be 0.05 divided by 0.025 would be 2 times. 0.06 divided by 0.015 would be 4 times. And then 5.89 times 10 power minus 1 divided by 3.68 times 10 power minus 2 would be 16 times. Now I know the change on the rate of reaction because of this is second order, which means that this would become times 2, 4. This is the change in the concentration, and this is the change on the rate of reaction. This is the overall change on the rate of reaction. So I would do 16 divided by 4, which is 4. And now this is the change in the rate of reaction because of chlorine. This is the change in concentration of chlorine. Both are the same. This is the first order reaction. This is a faster method, but you don't need to understand the concept for this. I did this method so that you could understand the concept. Right, next question. Use your rate equation and the data from experiment 1 to calculate the rate constant K for this reaction, include the units of K. Okay, simple, simple. Rate is equal to K times NO squared PLT. It says from experiment 1, which means that we need to use the concentrations of nitrogen monoxide and chlorine from experiment 1. So that would be 0.025 squared. Don't forget to put the squared. 0.015 and then rate would be equal to 3.68 times 10 power minus 2. So K would be equal to 3925.33. Now, how do I find the units for K? K would essentially be the rate divided, I'm just rearranging the equation here. The rate divided by NO squared times Cl2. That's it. What will be the unit of rate? The unit of rate is written here. Mole Dm minus 3, minute minus 1. I like to call it minus 3 and not mole per dm cube. Seems weird for me. This would become mole 2 dm minus 6 times mole dm minus 3. We use the function of indices, which means that if two things are being multiplied and they have the same basis, the powers get added. So 2 and 1 here becomes 3, and minus 6 and minus 3 becomes minus 9. So mole 3 dm minus 9. Let me just write this down. Mole dm minus 3 minute minus 1 becomes mole 3 dm minus 9. Mole gets cut here. This becomes 2. And then this goes upwards. The minute stays as it is to become 9. And then minus 3 plus 9 becomes 6. The 2 goes upwards to become minus 2. So this becomes, let me just do this again. Wait. I had mole dm minus 3 minute minus 1 divided by mole 3 dm minus 9. Why? Because this was mole 2 dm minus 6. This was mole dm minus 3. Together they become mole 3 dm minus 9. I remove the mole from here since I cut it down from this. So this becomes mole 2. Now I bring this entire dm minus 9 upwards. So now it becomes dm9 and not dm minus 9. So dm9 multiplied by dm minus 3 would essentially become dm6. So this becomes dm6 minute minus 1, and mole 2 goes upwards to become mole minus 2. So mole, since it becomes reciprocal, so mole minus 2 dm6 minute minus 1. The next question is NO2Cl is another compound containing nitrogen, oxygen, and chlorine. In sunlight, NO2Cl can undergo homolytic fission, okay, to release chlorine radicals, which can catalyze the conversion of O3 into oxygen. A lot of information here. Complete the mechanism for this process. Okay. Firstly, we use the first information that was given to us. That is that it can undergo homolytic fission. How do we undergo homolytic fission? We just convert them into two radicals. Homolytic fission is simply the formation of two radicals. So NO2Cl becomes NO2 plus Cl radical. NO2 radical plus Cl radical. Now, propagation step one. We use the second information which we have. We already used this also, that chlorine radicals are released. And if you were confused on how did I get NO2 radical plus Cl radical here, it's very simple. The question says that we already get chlorine radicals. That goes here. When this is cut, all I'm left with is NO2 radical. This is why I wrote NO2 radical here, which can catalyze the conversion, meaning the chlorine radicals are catalyzing the conversion of O3 into oxygen, which means this goes into oxygen. And now what am I left with? Always remember, in propagation, I will have a normal molecule, short for NM, and a free radical, which gets converted into another normal molecule plus the free radical. What do I mean by that? The normal molecule becomes the free radical, and the free radical in the reactants becomes the normal molecule. I had a free radical here. This would become a normal molecule, and the normal molecule would become a free radical. So O3 here would be converted into oxygen. This is done. Now one O is left, and the Cl radical is left, right? And now I'm sure that there needs to be a radical here. Why? Because I will always have a free radical in the product side in the propagation step. So now I know two things about this. It needs to be a radical, it needs to have Cl and an oxygen. That's it. Cl, oxygen, and a radical. There we go. Now we move on to propagation step two. The question says that chlorine radicals are released, which catalyze the conversion. This word is extremely important since chlorine radical here is acting as a catalyst, as we have learned. Catalysts can take part in a chemical reaction but remain unchanged and are reformed at the end of the reaction, which means that the Cl radical which we use here will be produced here. So I can write Cl radical right here. Now, throughout this entire paragraph, we never learned about the ClO radical, which means that it is an intermediate. An intermediate is a compound which is not present in the overall chemical reaction. Is it present here? No. It is produced as a product and is immediately used as the reactant. There we go. Now, what we can do here is I can add an O3 here. Since organic reactions are extremely slow, right? And it is not possible for all O3 to be converted into O2 immediately. And for the catalyst to be like, okay, I can convert all of the ozone into oxygen. No, some ozone will always be left. And this ozone will react here. Now I would have a chlorine radical. I would have four oxygen atoms left, which would make two oxygen molecules. I'll repeat. NO2Cl undergoes homolytic fission to release chlorine radicals. This is done. So all I'm left with is a nitrogen dioxide radical, which becomes here. Now it catalyzes the conversion. Chlorine radical comes here again of ozone into oxygen, of ozone into oxygen. All I'm left here with is a chlorine radical and an oxygen. And as I said, here we knew two things. It's a propagation step. We always need a free radical at the end of the chemical reaction. And in this free radical, we should have a chlorine atom and an oxygen atom. Chlorine atom, oxygen atom, radical. All three boxes are ticked. Next, it's a catalytic process. Cl radical is the catalyst, which means that it needs to be regenerated. There we go. This is an intermediate. This comes into use again. Organic reactions are extremely slow. Ozone will not be used entirely in propagation step one. It will still be present, which will react with this intermediate to form 2O2 and Cl radical. Simple as that. It is a difficult process if you do not understand, or if you probably miss the word catalyze, or if you miss the word homolytic fission, or one more important step here to be understand this is an intermediate. Three or four steps are important, and if you miss even one, then the entire mechanism goes haywire. So yes, this was a pretty difficult one. I would say the toughest question till now, but you can solve this if you have the knowledge. Ozone reacts with nitrogen dioxide as shown. The rate of reaction is first order with respect to O3 and first order with respect to NO2. Suggest equations for a two-step mechanism for this reaction. Now, you should know, your syllabus says so as well, that you should know how to go from the rate equation to the slow step of the reaction and from the slow step of the reaction to the rate equation because the number of moles present in the slow step of the reaction are the powers or the orders of reaction. I repeat, the moles in the slow step or the moles of the reactants obviously which are present in the slowest step of the reaction are their respective orders of reaction in the rate equation. Let's understand what do I mean by that. The rate equation here is given in words. We'll write it in symbol. The rate is first order with respect to O3, which means that O3 to the power 1, which is simply O3, and first order with respect to NO2. Now remember, O3 has power 1, which means that in the slowest step of the reaction, which will be step 1, we will have 1 mole of O3 and 1 mole of NO2. And now what is the method? Or let's understand this. When we have a two-step reaction, you don't know what the first step is. But now I'll tell you what the first step is. The first step will always be the slowest step of the reaction. It's not something which you can get through books. This is a trick which you can use. If it's a two-step reaction, the rate of reaction is given. The examiner automatically assumes that you will use step one as the slowest step of the reaction. Simple as that. You have the rate equation. You made the slowest step of the reaction from the rate equation. This will be your step one. Why will it not be step two? There's no specific reason for that. If you make this a step two, then you don't know what is step one. You have to start from somewhere, right? You know the slowest step, you make that step one. You will always do that. But there's one problem. How do I know the product this time? This is the overall reaction. The way I do this, normally I teach my students, is that I just combine both reactants together. Meaning, if I have NO2 and O3, this becomes NO5. Simple. Now I know NO5 does not exist. This is why this is an intermediate. Can you see NO5 anywhere here? No. But is it produced in the React product side? Yes. And is it readily used in the reactant side in the next equation? Yes. So it's an intermediate. To be an intermediate, there are three conditions. Firstly, it should be produced as a product in one of the steps of the mechanism, and it should be used directly in the next step, number two. And number three, it should not be present in the overall equation. All three things are ticked. Means it's an intermediate. So what did I do? I used the rate equation to make the slowest step of the reaction. I had to start from somewhere, so I made the slowest step as step one. NO2 plus O3 becomes NO5. NO5 is an intermediate, so it needs to be directly used in the next step. Plus. Now, I need to have one eye on the overall equation as well while I'm making this. What do I mean by that? O3 was in the overall equation. I already used O3. Cancel that out. I already used NO2 as well. Here, 2 moles of NO2 are used, which means all I'm left with is 1 mole of NO2. I need to use that here. Since it's a two-step reaction, I cannot go any further. Next, did I make any of these two products? No. So simply write them down. N2O5 plus O2. Now you might be thinking, what a weird step, just write that down. You can actually confirm this. How do you confirm this? The way you confirm this is that you cancel the intermediates and you make an overall equation yourself. What do I mean by that? NO5 and NO5 is an intermediate, and now I make an overall equation. O3 plus NO2 plus NO2 becomes 2NO2 becomes N2O5. This is simply for your checking to see if you did it correctly or not. If this equation matches with this equation, you are correct. And it did. So we are right. I'll repeat this one more time. How did we do this? It's a two-step reaction, so you can follow the trick, which is to make the first step as the slowest step. How did we get to the slowest step? We got the slowest step by using the rate equation. So O3 plus NO2 becomes NO5. This is an intermediate since it's a product in the first step. It's not used in the it's used directly in the second step, and it's not a part of the overall equation. So NO5 plus NO2 becomes N2O5 plus O2. How did I find this out? I knew what the overall equation was. I had already used O3. I had used 1 mole of NO2. This is the second mole of NO2 which I use now. I did not produce either of the products in step 1, and I produced both of the products in step 2.